All right, everybody, welcome to Electron Transition and Configuration Day. Today we are going to go over the different configuration models of single electron elements as well as multiple electron elements and try to demystify a lot of the confusion that comes with this chapter, because there's a lot of information. Now, we've already covered a lot about light and how light and energy are directly interrelated with wavelength, frequency, and so on. However, with elements, we're going to talk a little bit about how these transitions produce light, right? And the only way that we're going to be able to do that is by looking at hydrogen only. So the best way that I can kind of explain this is, let's pretend we remember the configuration of a typical hydrogen atom, or if you've ever seen like Big Bang Theory or other, stereotypical representations of an atom, it should look something like this, right? Where you have the nucleus at the very center and all these orbits that surround it, okay? And all these orbits, what we're going to start calling our shells, okay? So we have the n equals 1 shell, the n equals 2 shell, 3, 4, and all the way to infinity, pretty much, mathematically, not in practice. So we have this nuclei at the very center, and what I thought was a good way to kind of explain how Bohr's model came out is, let's kind of cut down the middle. So if we cut down the middle and we take that red zone, we get what we've been working with, right? Which is Bohr's model. And at the very bottom down here, if you look close enough, you would see, look, there's the nuclei. But you may be thinking, well, the nuclei is just a proton. Right? Well, that's okay, because remember, we're dealing with just hydrogen. Hydrogen in and of itself has only, or at least one of the isotopes, is just a proton. Okay? So when we're dealing with single electron elements, we have a few kind of situations that allow us to do quantification or the calculations a little bit easier. So when we were talking about producing or absorbing light, it all involves Bohr's model. It always involves just hydrogen. So when we get onto the multiple electron systems, we are not going to be talking about light anymore. We're just going to be talking about how a multiple electrons can be configured in an atom. All right, but here we're going to be talking just about hydrogen. Now again, hydrogen, I want you to again think of these shells as being ways for the electron to exist. Now remember, each of these jumps is a discrete jump in energy. Okay, so as we go up, we need to have the exact right amount of energy in order for us to go to that next step. So for example, let's say we have our ground state electron here on n equals 1, and to get to n equals 2, we need the exact right amount of energy, right? The difference between these two steps here, right? Whatever this is, whatever that E1 is, right? Now, we aren't going to be doing any of the work with the quantification of this, but I want you to really try to grasp your head around this. When we looked at the images of emission versus continuous spectrums, we saw that the emission spectrum of hydrogen had very unique bars that were emitting, right? Those bars are the unique transitions of the hydrogen's transition states. Whereas with a continuous spectrum, it's all present, right? So the sun emits a continuous spectrum. So all these energy jumps are different. So as you may have noticed, I said a word here. N equals 1 is ground state. Now, this should kind of make sense. Let's talk about why we call this ground state, and anything above n equals 2 is excited state, including n equals 2, excited states. All right, n equals 2, n equals 3, n equals 4, all these are excited states. So we consider n equals 1 the ground state because the electron that is in the ground state is closest to the positively charged nuclei, right? So imagine yourself, right? So you're an electron, and you're coming into this, very different element, right? But you really want to get as close as you can to the positive. So where would you go? Remember, positive and negatives, opposites attract. Well, the closest you can get is to this ground state. This is the closest an atom will let you get. So you want to be ground state. You don't want to be an excited state. You want to be chilling on the couch, watching Netflix, doing whatever, right? But sometimes there's just the right stimulus to get you to become excited. Okay, so new video game comes out, you got to go to the store to buy it or something like that, whatever the analogy calls for. So in our case, it's a very specific type of light. Okay, so a light wave comes in, excites the electron, right? Because the electron absorbs the energy of that photon. So the photon excites the electron, but remember, this photon has to be the specific wavelength in order for it to be absorbed. If not, it's going to go right through. Okay, because what will happen is, let's say it was enough energy to get it to here. Okay, if it got all the way up, it will come all the way back down and the light ray will be reproduced and go off, right? The electron has no way to absorb it. It has no level to step on, right? Whenever you're going up a staircase, you can't take half of a step, right? You have to go up an entire step, okay? Now, you could go up 2 or 3 at a time if you wanted to, but normally you just do 1. So let's pretend it's just 1. So it's just the right amount of energy to go up to our n equals 2. All right, so we're at n equals 2. And this absorption should give us our first clue, right? When we're absorbing energy from the surroundings, in this case in the form of light, we are going to go up in energy. So when we have an arrow going from a lower state to a higher state, that is an absorptive process. So we're absorbing energy in our electrons from a lower ground state or from any state to a higher state. So any arrow, if we went from n equals 2 to n equals 5, that is an absorption. From n equals 4 to n equals 5, that is an absorption. So on and so forth. Okay. If we went in the other direction, as I've already alluded to, let's say we went from n equals 2 to n equals 1, right? This is more of a systematic process, right? Everything, as I said many times, everything in the universe wants to be lazy. So if it goes from a higher state to a lower state, that is a spontaneous process. It wants to go back down, right? You go to the store, you get your new game, you come right back to the couch to play, right? That is the ultimate process. It wants to come back down to ground state because that's where it wants to be, right? It's the lowest energy. So it comes back down to ground state, but as we've mentioned in the laws of thermodynamics, energy cannot be created or destroyed. So the energy that electron possessed has to go somewhere. So what got it to that energy state in the first place? You're right, hopefully. It was a photon, right? A photon was able to excite that electron up to a higher energy state, to one of its excited states. And if it comes back down, it's going to emit the exact same photon, right? It's going to emit the exact same photon. So it emits out another photon. All right. So when we go from a higher energy state to a lower energy state, it emits a photon. So we lose a photon. All right. So a lot of questions in chemistry pertain to the relationship between this energy jump and wavelength or frequency. Now, I'm just going to focus on wavelength because frequency, I think, is very parallel to that of wavelength, but wavelength's a little bit more tricky. So let me give you a few examples here. Which one of these transitions is an absorptive process, meaning it absorbs energy? Is it arrow number 1 or arrow number 2? Take a second. Arrow number 2, that's right. Arrow number 2, right? So arrow number 2, we go from a lower state to a higher, so we absorbed a photon of energy, okay? Now again, these arrows are representative of an electron going from a lower energy state to a higher energy state, or going further away from the nuclei. All right, now let's make it a little bit harder. Let's say we have that arrow here, this arrow, and let's make it this arrow. All right, so we have these 3 arrows, arrow 1, arrow 2, and arrow 3. Which one of these is going to release a photon with the greatest amount of energy? Which one of these 3 arrows is going to release a photon with the greatest amount of energy? Take a second. Right, did you say arrow 3? Arrow 3, right? Why? Because we went down the y-axis the most, right? So we've covered the most y-axis. We've covered the most amount of energy in that transition. Now, this kind of alludes to something here, but you may have noticed that the jump from n equals 1 to n equals 2 is the biggest jump, right? To get off the couch is the hardest thing to do, but once you're off the couch, getting into the car, going to the store, all of those processes become easier, right? So n equals 1 to n equals 2 is the biggest jump. So if ever it incorporates n equals 2 to n equals 1, that is the biggest jump that you can take for an electron of a single electron element. Okay. Now last question here, and then we'll move on. Which one of these arrows absorbs the wavelength, a photon with the longest wavelength? So which one of these arrows absorbs a photon with the longest wavelength? So here are your 5 arrows. Okay, so we're looking for the longest wavelength. So take a second, think about it. All right. So there's a few things that we can do. I'm not going to give you the answer right away. I want you to think about it. So if we're absorbing a photon, right, is our arrow going up or down? Up, right? Yeah, it's going up. So if it's going up, I can eliminate 2 and 4 right away because our energy should be going up. We're absorbing energy. The atom, the system is getting more energetic. So then since we're going up, I'm looking for the thing now that has the longest wavelength. But if you remember, this isn't a y-axis in terms of wavelength, it's in terms of energy. So what did we say the relationship was between wavelength and energy? Indirectly proportional, yeah? So it's indirectly proportional. So as our energy is smaller, our lambda is larger, okay? So I'm looking for the shortest jump in y. So 5 is out, 1 is out, 3 is our correct answer, okay? If you had trouble with that, try following along one more time, replay that, and then also try some of the practice problems. All right, now you may have noticed something. This dotted line, n is equal to infinity. I want to talk a little bit about this. So we go from n equals 5 to n equals infinity because every single line is just going to get closer and closer and closer and closer and closer to n equals infinity because we're effectively getting smaller and smaller increments as we get closer and closer to infinity. All I want you to know is that in calculations or in theory, when we plug in this n is equal to infinity into our calculations or into Rydberg's equation, but again, we're not using it, but into Rydberg's equation, we learn the amount of energy needed to ionize. So this is where the electron is effectively ionized. All right, now let's think about this conceptually. If we reach that point, if we reach n is equal to infinity, we have gone so far away from the nucleus of the atom, or specifically in hydrogen, that it is gone, right? Remember, ionization means the removal of the electron from the atom. So if we get to ionize, that means we've gone so energetic, that electron has gotten so energetic that it has effectively ionized or removed itself from the atom. So in calculations terms, if we plugged in n equals to infinity, we have ionized the electron. All right, so enough of that. Let's move on to multiple electrons. Now, I'm trying out this new method of teaching this. Usually I start with the foundational work. Here I'm saying memorize this, because eventually we're going to cover that foundational knowledge. And so we'll see. So please bear with me as we try out this new method. So, although you don't really know, do you? So you're like, oh yeah, he's teaching me this, right? So whatever, just follow along. Okay. So in our single electron, right, we had our hydrogen atom, we had our n equals 1 shell, n equals 2, n equals 3, 4, 5, and so on. However, with multiple electrons, those shells are kind of broken up. So think about this as our n equals 1, and this is our n equals 2. All right, but now, because we have multiple electrons, we can kind of zoom in, if you will, right? So think about it as if this is our n equals 2 here, I'm zooming into this line, and it produces these 4 different orbitals. Now, that's a new word, so let's talk about that. Okay, so each of these orbitals can contain up to 2 electrons. Now, up to. It can either have 0, 1, or 2. It can never have more than that. All right, and that's just a foundational thing about orbitals. So with S's are spherical. All right, so they're spherical, meaning that if you zoomed into the center, the nucleus would be right smack dab in the center, and the 2 electrons, if there are 2, would be occupying it at some point in the sphere with a 95% certainty, which means that there's a 5% probability that the electron may be outside of this sphere, albeit it's a lot smaller as we increase the distance away from the sphere, but a 95% chance you're going to find that electron in that sphere of influence. Okay, again, you don't need to know those probability numbers. So this is an s orbital. A p orbital is what we call dumbbell shaped. Okay, so it kind of looks like a dumbbell. And the reason we have 3 different p orbitals is because we have 3 different dimensions. So we have in the y dimension, we have it in the x dimension, and then let me redo this one. I've done way too many p orbitals to allow that. And this is the x, and then we also have one in the z, right? So imagine this point here is coming towards you. It's coming out of the screen. So these 3 p orbitals exist because there's enough space for them to fit around the nuclei in 3 different dimensions. So imagine in the center is where the nuclei is, and the electrons that occupy this orbital are somewhere inside this orbs at a 95% probability, meaning that there is a 5% probability that is outside. But again, the further away we get, the less and less likely it becomes. Okay, so there's our 3. Now, there is more to this. So these are our P's, sorry. There is more to this. We have D, but we will not be working too much with D's. All right, because D's are a little bit too complicated for us. So we're not going to bother too much with them. So there's our D's, and then we also have this fun one. This is my favorite looking one. All right, it's so this is clover shape. It's just not a good looking clover. Clover, and then dumbbell and donut is I think what they call it. They're not very creative. All right, but again, we're not going to be working too much with these, so don't worry too much. So again, we have these orbitals, and each of these orbitals can again contain up to 2 electrons. So when we're filling this in, right, I know you don't understand why this is specifically the layout that it is, but we'll talk about more of this later. But I want you to just know that this is how all elements start. This is their very beginning when we're filling up their electron shells. This is how they'll always begin, and how every element has this at the very beginning. So if you were an electron and you came across an atom and you wanted to figure out where you were going to stay, which one of these orbitals, the question would become, well, which one would I choose? Okay. Well, I would choose 1s as my first one. So an electron comes along and it's wondering which one should I go to? Well, it's going to choose 1s. Can you think about why? Right? Why would 1s be the orbital that the electron wants? Right? Maybe it has to do something with energy. Right. Yeah, it's the one that has the lowest amount of energy, right? So every electron, everything in the universe wants to be lazy. So if it can stay in the 1s, like think of it as like a penthouse, it would be really nice for it. If we had another electron come by, it would occupy the same point. Same with the 2s, right? But here, when we get to 2p, so if we had 4 electrons, that's the order they would take. The first 2 would go to 1s, the next 2 would go to 2s, and then we come to these 2p's. So each of these p's all are on the same line in energy, meaning that if I were to fill them up, there's no preference for which one is which. So the analogy I like to use is, if you were a student going into your dorm room for the first time and your RA says, here are 3 rooms, all of them are equal, all with the same view, all with the same amenities, nothing different about them, which one would you choose? Well, if there's no differences, then you would just choose whichever one. It doesn't matter. So let's choose this one. All right, now let's pretend you're the second person to come in. All right, you're the second person. The RA says, well, one person already chose 1 room. Would you choose one of the 2 free rooms, or would you choose to bunk up with the first person? Well, if I was going into college and I was trying to choose the correct dorm room or choose a dorm room, I would choose the one that's empty, right? I don't want to bunker up if I don't know if I'm going to have, I could maybe even have my own room. So yeah, so electrons think that way too. So if the third person comes in, exact same philosophy, goes into that third room. All right, now the fourth person that comes in, or the fourth electron here, gets to choose whichever one, but again, same principle. They're forced to bunk up at this point, okay? So you may be wondering, well, how many electrons do we really even have? So if we ever have 2 or more electrons, this is the configuration I want you to show. All right. What I'm going to do here is I'm going to pause the video, and we will continue with electron configuration in the next video.